Good morning, pre-cal students. Uh, I was going to say, I hope you're enjoying the cooler weather. If you're not, it won't matter because I'm sure next week it will change to something else. Um, I think that once we get over the initial shock, the cooler weather can actually be very, very invigorating, but it is so crazy how the weather evolves in this area. And so the saying that I heard when I moved to the area is don't worry about the weather, it'll change in 30 minutes. And I think that was pretty much the case in College Station where I was when I lived there and went to grad school. But of course, when I've been in Houston, it's even more uh, uh, apparent because, of course, we're closer to the water, so we get all kinds of weather. But I hope that you're enjoying that and that the change is good for you. Now, remember, next week we will have our third test, and I will post tomorrow a announcement on Blackboard, an announcement that will cover basically the window of time, just like the previous two tests, and also what you expect in terms of coverage. So just remember, this test will be completely devoted to the trigonometry. So we'll start with chapter 5 and end with what we talk about today. So maybe that's good that it's focused on one topic. Certainly after the third test, there'll be some trig and then some newer items from the conic sections. So the luxury of just one topic test won't last for very long. And I guess that's what you're used to being college students. What we want to do today is to now add the inverse trig functions again, just to see how we can utilize the maybe triangles to further our understanding a little bit. No, of course, nothing's changed. The reference number, the reference angle, all the arithmetic, the Pythagorean identities, the Pythagorean theorem, all of that stuff meshes together. So there's no difference. And I always tell students, I said, you are at your own disposal to utilize triangles. Triangles are obviously part of certain problems that we have to solve, but when you're working with the trig functions, you can utilize any method you like. That is not something that you have to do. So again, I think the main thing here when we talk about utilizing trigonometry, we have the triangle approach, which helps us solve other problems, but we certainly don't forget where we've come because again, that was our foundation, so to speak. And so what I want to do today is now start with the inverse trig and then segue into one of our triangle theorems called the law of sines, which I think you'll find to be very straightforward and useful. A lot of the triangle theorems, again, they don't directly impact the calculus so much as that they impact a lot of what we do when it comes to working with in your STEM classes, like for instance, if you were working in a physics class or an engineering class. So that's where we see the utility of those theorems more. But they're mathematical objects, so you need to learn how to use them in this class. So let's start with 6.4, and we'll say inverse trig, and trig short for trigonometric inverse trig functions again. So every time we learn something new, and that's really the routine in math, you keep studying the same things and you basically go back to the old topic and add more stuff to it. And that's pretty much how you do math. And that's any discipline is pretty much like that. So what I want to do first is just use an independent variable x and review some of the ideas that we have that we've already constructed for the inverse trig function. So let me adjust this just a little bit, if it's just right. There we go. So the inverse sine function we'll just say y is equal to the inverse sine of x. And of course, your Google calculator uses the arc sign, so you'll get familiarity with both. I like to use this, but the arc sign is fine if you would like to use it. Now, again, this reminds us of what we did with the logs and exponents, not necessarily the inverse equations, but just writing the inverse relationship between the inverse sine and the sine. So if we take sine of both sides, we use the inverse equations here, the sine of the inverse of sine being x. And then, of course, in that case, you know that x has to live between -1 and 1 for this to be true. So we have x between -1 and 1. That is, it must be in the range of the sine function. And then, of course, where does y live? What's the range of the inverse sine function? That's -pi/2 to pi/2. So these concepts that we have here in our construction process will directly impact how we work with triangles. So it's important to know these and go back. So what I'll do is we'll do the 4 that are the main ones: the inverse sine, the inverse tangent, the inverse cosine, and the inverse secant. And of course, the inverse cotangent and cosecant, they're fine, but we just don't give them as much time. So let's go ahead and look at the inverse cosine. Again, whatever letters you use is up to you. You know that WebAssign will specify a certain variable, and if the variable has to be used in the response, you must use that same variable. But as you work, you feel free to do whatever variables you like. Sometimes it's better to stick with the WebAssign variable as opposed to getting confused, unless your translation is easy to do. So here, we'll say that y is equal to the inverse cosine of x if and only if x is equal to cosine of y, applying the cosine function to both sides and using the inverse equation. And then, of course, where does this make sense? Where x is between -1 and 1, and where is the what is the output of the inverse cosine function? Well, by our construction, it lives between 0 and pi inclusive. So again, one thing I said when we first started this, you can just remember what the graphs are, and that gives you all this information. So how you want to remember this is up to you. I think this is convenient because it's easy to write down, and the graph you can just kind of keep in your brain. And then number 3, we'll do the inverse tangent. Again, if we apply the tangent function to both sides, we get x is equal to tangent of y. And what are the restrictions? Well, this is a very user-friendly function. We remember, in this case, that x is any real number, -infinity to infinity. So it's really hard to mess up the inverse tangent function. And then, of course, the y's live between the horizontal asymptotes, -pi/2 and pi/2. Again, these are pretty strange functions, and they will be strange until you are very comfortable with these and the identities that I've already taught you. We will use them over and over. And basically, any of the arithmetic of the unit circle, we will continue to use. And then the last one, just to give it some airtime, so to speak, will be the inverse secant, because we certainly talk about this in the calculus sequence. And this had the Dr. Larson definition here, and also the definition of the some of the online resources for inverse trig, especially the Wikipedia page, which I've recommended to some students. It's an excellent expose on the inverse trig functions, the calculus, the series, and all of that. It's very well written, and of course, it's public domain. So we get x equals secant y. And then what were the constraints? Well, remember, I'll use the absolute value this time. X could be 1 and greater, or it could be -infinity up to -1. So we can use the disjunction here. So it just goes in 2 directions, 1 out to infinity and then negative infinity up to -1, but leaving out the -1 to 1 exclusive. So we have that gap. And then, of course, the output mirrors what we have for the inverse cosine, but we leave out pi over 2, which is the horizontal asymptote. So again, this is based on the construction for the inverse secant function. Now, when it comes to solving equations, we're going to spend some time with these two guys here. We have what we call, ladies and gentlemen, the law of sines, which obviously will require us to think about the inverse sine function. And we also, after that, next week, we're going to talk about the law of cosines. So it's going to impact this function here. So when it comes to the unit circle, sine and the cosine get the most attention because they are the most important. So what do we get here? What are the new ideas that we get? Well, what I want to do is just write down a very simple example. I'm going to write a right triangle that has the sides measured. So just go ahead and draw a right triangle. Again, the right triangle is distinguished by the fact that it contains a right angle or an angle of 90 degrees or pi over 2 radians. And so in this case, we're given that and here I'll go ahead and mark where our theta is. Of course, we get two acute angles, and the theta here is designated to be in this corner. And so the adjacent side is given to be 24. The hypotenuse is given to have 51 units, and then the opposite side is 45. Now, of course, these satisfy the Pythagorean theorem, so we do have a legitimate triangle. We're not here to do smoke and mirrors, so to speak. So when you look at this, what we call this is a Pythagorean triple, and there are infinitely many of those. I mean, that's a number theoretic construct. So if any of you all become electrical engineering majors or math minors and you get to the university and take number theory, you'll discuss some of the Pythagorean triples in more detail. Now, what we want to do is just say, okay, well, what do we know about theta? What do we know about theta in terms of the standard triangles? Well, for instance, I'm going to write down 3 trig functions that appear out of this list. So we're going to have sine theta, we're going to have tangent theta, and also cosine theta. So relative to the theta here, we'll do opposite over hypotenuse for the sine. So we get 45 over 51, and then we'll reduce some of these. And then for the tangent, using ratios of the sides of the triangle, we will get opposite over adjacent. So we have 45 divided by 24. And then lastly, the cosine will give us adjacent over hypotenuse, 24 over 51. Now, if we look at these, they can be reduced because they all have 3's in them. So 3 here, that'll give us a 1 and a 15, so that'll be a 5. And 3 here, that'll be a 1 and a 21, so we get a 7. Same thing here, divide by 3, we'll get a 15. Divide the 24 by 3, we get an 8. So again, these are relatively prime. And then here we get an 8 and a 17. So we've just written down 3 trig functions relative to theta. We could write down 3 more if we wanted to. So that's a simple construct altogether. But what we notice here is that just like what we've done up here, we have the corresponding inverse trig function. So these all make sense. I mean, you know, of course, the sine of theta could equal this. I mean, it's a number between -1 and 1. Likewise for cosine, and then tangent of theta, that can be any real number. So we don't even have to worry about that. So if and only if theta equals the inverse sine of 15 over 17. Now, you know, you don't have to use the parentheses, but when you do the Webasine, they build them in. And so you don't get confused with the negative. It's okay. So here, if and only if theta equals the inverse tangent of 15 over 8, and then we can have theta equal the inverse cosine of 8 over 17. Now, again, when you look at this and you're thinking, well, these are exact values, and then it's like, well, if we interpret these as, again, the outputs of the trig functions, then you know, these are pure numbers. And so we might be thinking, well, we could use any of these three because these are all things that we could compute or approximate with the Google calculator. And of course, we have the reciprocal identities too. So we're able to do any of the trig functions. But let's just look at an example here. Let's just say that we use inverse sine to find the angle here. Now, I want to do this two ways. For instance, if I'm just going to write a little extra here, if we're thinking of doing this in degrees and staying in the radian mode, we can say, okay, well, theta in degrees would just be inverse sine of 15 divided by 17 radians. And then, of course, we would convert to degrees using the conversion factor. And now, of course, we could do this so that would be one way to do it. And then, of course, we could just be in the degree mode, which we found to be very useful when we have lots of trig functions and we just don't want to write down the conversion factor. But I just want to show you that you always have the power to do whatever kind of computation you want. So if we stay in degree mode, and we know we're in degree mode, we don't even really need to put the degree there. We can just say, okay, we're in degree mode. So this is going to give us an answer in degrees using the calculator's ability to convert for us. So that's what I want to show you because we're going to be doing some approximations today. So now if we go to our Google calculator, and let me move some things around so it'll see it. It's not a bona fide web page, and so the my Zoom doesn't always want to see it. It's so crazy. So here we go. There we go. Now it sees it. So let me move Professor Ron over. So now here, let's just say that we stay in the radian mode, RAD, mainly we'll be in degree mode, but I just want to show you this. So we're in degree mode, or excuse me, radian mode. So we're going to use the inverse sine. So that'll be arc sine with the Google calculator, 15 divided by 17. And then we're going to multiply by the conversion factor, 180 divided by pi. And this will give us 61.9275. And then, of course, in this case, let's just say that we wanted to round to 1 decimal. So I'll write this on the page when we come back. So you'll see it round to 1 decimal. Say Webasine instructed this. We know Webasine will often instruct us to approximate. And that's the only time we approximate. And so we would, in this particular case, say this would round to 61, in this case, 0.9 degrees. Now, of course, I just want to remind you of what we already had that we've used before. We could say, well, you know, I'm gonna avoid the conversion factor. focus on other parts of the problem and let the calculator do the conversion for me. And so now I'm thinking I'll switch to degree mode, and I'll just say now inverse sine. So that will be the arc sine of 15 divided by 7. Excuse me, 17. We certainly don't want to divide by 7. That would not even be defined. And so we get the same answer, 61.9275. And of course, that'll round to 1 decimal as we had before. So I just want to make the point here that the work that we're doing is all consistent. So we're thinking when we look at this problem here, and we say, okay, well, you know, same deal, everything's good, Professor Ron, but we're thinking, why is it that we get first quadrant angles, so to speak? Well, first, if we look at the sine, we go up here and see that if we've got the positive input, we're going to get radian measure between 0 and pi over 2, or we're going to get degree measure between 0 and 90 degrees. That's what the sine function is going to do for us. Now, had we used tangent, that would have been the same thing. If we had a positive input, then that's going to put us between 0 and pi over 2, just like the inverse sine function. Now, if we look up at cosine, a little bit different, but still the same thing. We notice in this case, we still have the positive input will give us an angle between 0 and pi over 2. But then, of course, if we got the negative input, that would throw us into the second quadrant, pi over 2 to pi. In these cases, we get pushed into the clockwise arguments. That is, these become negative. So again, we have to respect what the inverse trig functions give us, and then make any accommodations based on that. Because WebAssign might say, well, you know, I want your solution to live in this interval. And so then we would have to make corrections to find something coterminal to that would live in a particular set. So when I mentioned this about knowing this, that's not an option. If you understand the inverse trig functions, you must understand at least the basic rudiments of them, being the ranges in domain, and then of course some of the inverse equations, and then of course the equations involving the negative argument. I mean, these are indispensable. And so it does you well just to write down things you know about these functions on note cards, and then the next day you get up, write the same thing down again and talk about it, teach it to the wall, or teach it to a friend on Zoom who's struggling with this, because these are very important concepts. So now what I want to do is take this idea and look at an example. For instance, you know, say we just want to compute. We're thinking, well, now these inverse trig functions give us equations, and we're thinking, okay, well, let's learn how to solve some basic equations and see if the triangle helps us, or the definitions that we have here help us. So here's an example. We'll do a couple, and then we're going to derive another Professor Ron's lemma that we're going to need for the law of sines, and of course, solving equations in general. So here's what I have. Compute. Now remember, if WebAssign says give a solution in degrees, you can't just type 45, okay? You have to do 45 with that little superscript O, okay? That way, WebAssign knows you mean degrees. Radians are pure measure and degrees are pure measure, but we have to denote the difference with that little superscript, okay? And I know that it's easy to forget, but just remember, if they say give an answer in degrees, or the set is in degrees, you must denote that. So don't make any assumptions about anything. Oh, WebAssign's going to know that this is this way. No, they're only going to know. WebAssign will only know if you type the response in a way that WebAssign will understand it. So here, what we want to do is compute theta, and I'm going to put in degrees here, 0 degrees to 180 degrees, such that in this case, I'll go easy on you, or maybe I won't go so easy on you. I'll switch it up a little bit. Cosine of theta equals, let's just say, negative 5/8. I'm just going to throw in more negatives today. We don't get so many negatives with triangles, but just to kind of throw this in to help us out a little bit. Now, you look at this, and first we say, well, okay, if and only if theta equals inverse cosine of negative 5/8, okay? And then you're thinking, okay, well, we can leave this alone, or we know the inverse cosine of a negative angle, and it's gonna, so when we look at this before we move on, look, inverse cosine of x lives between 0 and pi. So when we think about the unit circle, here we have x is less than 0 and x is greater than 0. So we expect the output for this equation to live in the second quadrant. Again, because of the definition of the inverse cosine, it's a one-to-one function. And so when we look at this, there is only going to be one value in this equation, one output. Now, again, when we look at this and we look at this, they coincide. So we don't even have to worry about doing any additional analysis because these two sets are the same. So we only expect one solution here. It's not so simple for the sine function, and that's kind of going to be a thorn in your side. So here we expect one solution. So now, if you like, you're thinking, so it's going to live in the second quadrant, we can just go ahead and say, well, this is the inverse cosine of the negative argument, so we can write the identity. But since we're going to use degree mode, let's switch the pi to 180. So we get 180 degrees minus inverse cosine of 5/8. Remember the theorem, we had the pi minus the inverse cosine of x, but now we're in degrees. We'll just go ahead and switch to that. And just note now that we are in degree mode. So when we look at this, this is an exact representation of the solution, but say our client wants an approximation. So at this point, we can say, okay, well, let's go to our Google calculator. And so again, note that we have the DEG for degree mode. It will do the conversion for us, so we don't have to multiply by 180 divided by pi. So we'll do 180 degrees minus inverse for cosine. So that gives us the arc cosine, 5 divided by 8. This is the way I can get you used to this notation without having to use it. So thank you, Google Calculator. Again, you may like this better than the -1. If you like it, use it. Just don't, just like I say, WebAssign doesn't mind arc cosine. If you typed arc cosine instead of cosine superscript -1, it doesn't care. It knows that they are the same. So here, when we look at this, we get 128.682. That's just 3 decimals. And then, of course, in this case, I'll say round to 1 decimal. And so this will give us, we're answering this question, 128.7 with the degree. So again, if you were doing a WebAssign problem, and you wrote 128.7 and no superscript, when you know it's a degree, then it would be marked wrong, and shame on you. Okay, you know better. The thing is, if we are working in a context where we're thinking of conversions and we know what the numbers mean, that's fine. But when we're working with a computer algebra system, we have to be very specific because our computer algebra system treats dimensionless numbers as radian measure. Okay, so even though the degree measure, you know, with the units or degrees, it's a fabrication. It's still a pure number, but we still have to denote that here, meaning. And then you think, man, if we did graphs with degrees, we'd go crazy. Degrees and graphs make no sense, but degrees and radian measure perfect sense. Okay, but we are stuck with degrees. We are stuck with them. So there's our solution for this equation, and we have found all of them. Let me re-emphasize, we have found all of the solutions because these two sets coincide and it's 1-to-1, so there's only one solution. Okay, so that's really important. And later on, we're going to talk more about the cosine function and its solutions when we get to the law of cosines. So now, let's just kind of look, open Pandora's box and see if we can make the problem more complicated, and we will. So here's an example. So what I've written here is theta to live. We're going to look at the lower quadrants, 180 degrees to 360 degrees, such that in this case, sine of theta equals -4/5. Now, first, if we just analyze this a little bit, it's gonna be different from what we did up here. So we can think, okay, well, 180 degrees to 270, those are like the boundaries, so to speak. The interior of this, excluding the endpoints, defines the third quadrant. So this is quadrant 3. And here we know that y is negative. And then, of course, if we look at quadrant 4, so excluding the endpoints, even though I don't want to kick them out because the problem came to us that way, we have quadrant 4, the interior of this interval, where y again is negative. So what we're seeing here is that we have a complexity that we didn't have with the cosine function. So when we think about this, it's like, okay, oh, okay, well, let's just say this: inverse sine of x lives between -pi/2, we'll do the, and pi/2, or we can say -90 degrees to +90 degrees. But this negative part here, -pi/2 to 0, that's in the fourth quadrant because that's a clockwise measurement. So these two correspond. So if I were to solve, or if we are to solve an equation of this form, then the output will give us a solution in the fourth quadrant, because there's only one, because again, the inverse sine function is 1-to-1. But we know because the sign convention is the same for sine in both of these quadrants, and they have the same reference angle or number, then we have another solution over here that of course is not given by this. So that's a complexity, again, that we did not have up here, because again, the signs are different. So the sine function is more complicated when it comes to solving equations than the cosine function, which again, you know, this is what I basically had to develop when I taught trig the first semester at the South Campus. When I graduated, I was using the Teague textbook, and there was no formal statement of what I was trying to teach them. In the book, they just drew pictures. I said, but that's useless. If you don't have nice numbers, it's not going to help the student know what they're doing. So I developed this, but I also tried to, once I got to the North Campus, is to try to develop a reason for it that's not going to use items that we haven't studied yet. So that's one thing I had to change from the first time. I used an identity, a subtraction formula, which proved the result very nicely, but I thought I need to come up with a way to justify it using stuff we just know at that point. So, and sometimes that's possible. So now when I look at this, or we look at this, we're going to have if and only if theta is equal to the inverse sine of -4/5. Now let's just think about this and look and see what it actually says to us. We know that the inverse sine function is odd. So this gives us negative inverse sine of 4/5. But again, when we look at this, this is in the fourth quadrant, but it's less than 0. So we say element of the fourth quadrant, but negative sign here, that lives here. That's an element of this particular set. We would say, if we're thinking degree mode, -90 degrees to 0 degrees. So again, we're going to think degree mode. We're assuming that, and that's not where we want to be. So in order to get the correct theta here, and we're thinking, okay, we want theta to live here. You know, we want to solve this, so we can say that, and I had to do this before, that's really going to be our theta1, isn't it? Because it doesn't live here. So this is really a theta1 in this case. So this implies that the actual theta that lives here will be 360 degrees, add to make the coterminal, but to put it into the positive realm, minus this guy. And now this lives where we want it to, between 270 and 360. So that's a check there. So the inverse sine function and how it deals with things is really no walk in the park. Let me move Professor Ron over a little bit. Is no walk in the park. It gives us all these pains to have to deal with. And so now, okay, all right, so we have a solution, and we're thinking, all right, well, let's just go see what it is. We got one of them. So we can clear this out, and so we'll have degree DEG 360 minus inverse sine. So we're going to use the Google calculator for our calculus approximation of 4 divided by 5. And this gives us 306.8698, etc. So we're going to round again to 1 decimal. I'll just write this here. Round to 1 decimal. And so this will give us a solution of 306.9 degrees. Okay, well, that wasn't so bad. That we made whatever adjustments we needed. So you can't just say, okay, well, here's the inverse sine and ignore the definitions. The idea here is that this is where it all begins, right here. So we have to respect this definition. I mean, we can ignore it and then just write down a bunch of nonsense. Now you might be saying, so if we think about this, I'm just going to draw a little picture of part of the unit circle here. Well, I'll draw the whole unit circle, just kind of freehand it. And that's a Charlie Brown head. That's a terrible unit circle. Sorry, that looks more like an ellipse. But that's okay. Well, not Rembrandt, but that doesn't even, that's just terrible, period. So here we go. So we're thinking, let's just use an alpha and a beta. Those are my favorite Greek letters aside from phi and theta. So say we had an alpha here. So here's an alpha, and it solves sine x equal b. And then here, by symmetry of the sine function, because the sine convention is the same in the third and fourth quadrant. So here's 4, and here's 3. And then as we move around here, this gives us beta. So what we know is, it's like we computed alpha. We can think of this as alpha. Sine of alpha equals b. I'll just say solve this equation. Here our b was -5, 4/5. And sine of beta equals b. And then we'll say, what is beta? Well, then you say, well, I can look at the picture and draw it. I think I know what it is. No, you don't. You don't know what it is. It's not a simple construction here. But we can figure out the relationship between alpha and beta, which is basically the content of Professor Ron's lemma. So what we want to do is just think of the reference numbers. So now what do we know? Well, for instance, here, alpha is in the fourth quadrant. So alpha bar, we'll just go ahead and look at this in terms of, if you want, we'll do radians, then we'll convert to degrees. Since we're used to radians and all, then we'll convert this to degrees and have a degree formula. So this would be 2 pi minus alpha. And then beta hat, or the reference angle or reference number for beta, would now be what? Beta minus pi, because it's in the third quadrant. So this will be beta minus pi. But notice these are both the same angle in the first quadrant. So these are the reference angles. So the reference angle. So again, we've got values, terminal points here for the y values being equal by symmetry of the circle. And so therefore, we would look at the reference triangle, so to speak, and slap a negative on it to get the right value for the sign in the third and fourth quadrant, just like we always have done. But so what does this mean? These reference angles are equivalent. So we have 2 pi minus alpha equals beta minus pi. And so here, if you add, in this particular case, like add pi to both sides and subtract and add this, so what is this going to say? This says alpha plus beta. So bring this over and bring that over equals 3 pi. The sum of them is 3 pi. But that's 3 times 180 degrees, which is going to be 540 degrees. That's correct. So this note This is just 360 plus 180. That gives us the degrees. And so now so if we want to know what beta is, what's the second solution, if and only if beta equals what? 540 degrees minus alpha. So that gives the second solution that we were looking for in the third quadrant. This is our third quadrant solution. So now when we think about this and we look at this, we're like, okay, so what does that do for us? So now we say here, so equivalently, back to the problem, the second solution, we'll just say second solution equals, well, the first solution was this, so this is going to be 540 degrees minus 360 minus inverse sine of 4/5. So that'll be 540 minus 360, that's 180. So 180 degrees minus plus inverse sine of 4/5. So that's the second solution. So, I mean, you don't have to do all of this work. I'm just writing it out formally. We just basically say we subtract the first solution from 540. But let's just see. Let's just say now we have our Google calculator. So we'll stay in degree mode and just do 180 degrees plus inverse sine 4 divided by 5, degree mode, and that gives us, I'll write this down, 233.130 into one decimal. I'll just write 130. That's going to run us out to 233.1 degrees. So now, when we look at this, we have two solutions. And I'm going to state this formally. So now we can say, okay, well, 233.1 degrees, comma, 306.9 degrees, right there. So this is not a simple problem like the cosine function, basically because the output of the inverse sine doesn't agree with this. So that there gives you the additional complexity. And then plus the fact that between these two quadrants, the value of the sine, the actual positive negative part of the sine is the same. So we get two values that are equivalent relative to the reference angle. That is, the y values are equal. So we always have to realize, what does the inverse trig function give us? And then once we know that, how do we get the other one? Well, we see now that we need to write this down because this is actually important information. Again, this always works algebraically, and that's what the textbook that I was using at the time, and even the textbook that we use with Dr. Stewart, though I think it's a wonderful book, it does not do this. And so I thought to myself, my students need something a little bit more cogent than just, well, draw a picture and guesstimate. That's no good. And you need to be able to say, okay, here's one solution, boom, here's the other. Exactly. So let's go ahead and just state this in terms of what we mean here. So now, if we're going to write this down formally, so we'll just say solve sine x equal b. And for the first one, we'll say that we're looking at 0 to 180 degrees. And then, of course, you can think pi if you want. So this is what we call the upper arc of the unit circle, upper arc. So you'll say x is a solution. I guess it doesn't matter what you call it. We're just going to say x is a solution. And then this implies second solution. Again, we have to be in the quadrant. If you're on an axis, that's it. I mean, the axis, you're done. Your sine of pi over 2 is 1. I mean, there's nothing there. When you're on the axis, you're out of the quadrant. So that don't get confused with that. There's nothing difficult about that, but that never happens. And when it does happen, I think we just get afraid of it. And well, I don't get afraid of it, but you do. And you again write down nonsense. So be careful that we're working in the quadrant. So now, of course, we didn't do this proof, but it's easy. You see, they just differ by pi. The same kind of proof works. So a second solution will be 180 degrees minus x, or if we wrote this in radians, it would just be pi minus x with the radians. Now this, so if you wanted to do the same proof we did for the last one, you get the same value here. It's the same thing, do the same proof. For the lower arc, 180 degrees to 360 degrees. I'm just doing this in a very user-friendly way. Here's the lower arc. Then we would have, say, x is a solution. So one solution, like theta 1. This implies a second solution. And again, we're assuming that we're in the quadrants, even though my notation, I'm giving the entire upper arc and lower arc. You're in the quadrants. And now we're either in the fourth or the third quadrant. The second solution, as we just proved, was 540 degrees minus x, or 3 pi minus x if we're dealing in radians. So this would be degrees. This would be radians. Degrees, radians. So here you can think 0 to pi, and here you can think pi to 2 pi in radians. So we'll have plenty of opportunities. This is half of Professor Ron's lemma. That's what I called it then. And I actually had this typed up in a LaTeX document. I need to find it. And I passed it out to the class so they would use it. And then, of course, I just started making it part of my lecture. So when you look at this and you think about what we're doing, this actually turns out to be a plus, but we see that we get this result using the way we constructed the inverse sine function. Now, we think, oh, the inverse sine function is really nice and it's odd function. The graph is easy to remember and all, but the ease that we got from choosing that particular restriction certainly made this a lot more complicated just because of the nature of how we define the sine function. So with that said, is there going to be something similar for cosine? Absolutely, but it won't be in two parts like this. It'll be much easier, simple to do compared to this. Now, what I want to do is look at some other computations that we can do with the inverse trig functions that involve how we can utilize our new interpretation of the triangle. Now, you did one of these before. So for instance, I would like us to compute the cosine of the inverse tangent of 12 over 5. Now, before I got some messages from you, you might have something that's on the unit circle, like a 1 or a square root of 3. So you can go from the terminal point to the measurement along the unit circle very easily, because that's a terminal point you're familiar with. If you're doing, sine over cosine, you know those numbers. But this is not a number. This is not a ratio that we have on the unit circle, clearly. So the thing is that you think, how do I do this? I mean, I can use my Google calculator, but that's not going to help you. I want an exact answer. I don't want an approximation. And this confounds everyone. And I have students that still think I'm, the worst person in the world. How do you expect me to do this? Well, I'll show you how to do it. The idea, like I said before, is that if you understand the inverse trig functions and how they relate to the triangles, then this problem is simple. So since this is not something we recognize from the unit circle, we can just make a simple change of variable or a substitution. So this is the reverse path. How do we get to the theta, so to speak? So what we can do is let theta be the inverse tangent of 12 over 5. And think of this as a triangle. And so then, just like we did before, if this is true, then we can take tangent of both sides. So tangent of theta will now be just 12 over 5. So we think of this as a y over x in terms of ratios of a right triangle, that is opposite over adjacent. And so at this point, you could say, well, I can use the Pythagorean identities, or we're actually going to be much lazier than that, because that'll take more time. It'll be correct. I have no problem with that. It'll be correct. But now we can just apply the Pythagorean theorem directly. So we can say, okay, just draw a triangle. Doesn't have to be perfect. So if we mark our theta here, just like we did on the very beginning of the lecture, we can do opposite over adjacent. So 12 over 5. And then, of course, this is where the Pythagorean identity comes in, namely the Pythagorean theorem, which is not an identity, unfortunately, but, it's accomplishing the same thing. So 12 squared plus 5 squared, that gives us 144. These numbers are easy, plus 25. So that'll be a 9. And a 6 and a 1. So that's a perfect square. That's 13 squared. So by selecting the positive square root here, we get a hypotenuse of 13. So now when you look at this, you're thinking, okay, well, that's good. I can do this now. There's my triangle relative to theta, and I can do all 6 trig functions here. So now cosine of inverse tangent of 12 over 5 is cosine of theta. But cosine of theta is now just adjacent over hypotenuse. So we say adjacent over hypotenuse, and that'll be 5 over 13. So this is easy. This is truly easy, and it's made easy using the right triangle interpretation. So what we're saying is that where the graphs are a disaster with the triangles, and even the inverse trig functions are, once we know about them, we can use the triangles to make our work more efficient. And so, again, we think of a reference triangle. That is, as we move around the unit circle, sides of a triangle can't be negative. That doesn't even make sense. And so we really do have to force ourselves to think about the reference triangle that is legitimate in the first quadrant, and then we can assign values to the trig functions based on where the actual theta terminates. So if we're in the third quadrant, then the value of x must be negative and the value of y must be negative to write the correct ratios. So again, we preserve the geometry without making it nonsensical. So again, everything's the same. We just respect the fact that we have a right triangle and how it can simplify things. Now, one thing that you're thinking we're doing, what if we have an actual composition that's not a real number? That is, what if we replace the input here with a variable? Can we still use the same technique? And the answer is yes. So let's look at an example of this. That is, WebAssign will say, write an algebraic expression. So what we're doing is we're taking these functions that are transcendental based on pi and creating algebraic expressions out of them with these compositions. So there's a intimate relationship between the radicals and the transcendental functions because of the Pythagorean theorem. So write an algebraic expression for, in this case, secant of the inverse sine of x. Now, when you look at this and you think about what this is saying, you're like, okay, well, the inverse sine, that lives between negative pi over 2 and pi over 2. So we'll say like inverse sine lives here. And as long as I stay away from the endpoints, the secant function has positive values there because the cosine in the quadrants here, namely fourth and first, is positive. So this tells us that this particular expression should have a positive value. So that we kind of get that from the very beginning. So we're seeing that this implies that secant of the inverse sine of x should be positive if it's going to make sense with how we've constructed the inverse sine function. So now we do the same thing we did before. We can say theta is equal to the inverse sine of x. Now, of course, you can go directly to sine theta equals x if you want and leave out this step. It doesn't matter. It's probably good to write it though. So sine theta is just x. And you can write a 1 downstairs to write a equivalent ratio. You could do 2x over 2. You could do pi x over pi. I mean, that's kind of ridiculous. All you have to do is preserve the ratio and the numbers make sense. So now when we look at this, it's exactly like what we have here. This is just opposite over hypotenuse. So we're seeing that the ratios of the sides of the right triangle correspond to how we determine the definitions for sine and cosine in the unit circle. So we can do the same thing again. Think of a reference triangle, theta, and then opposite over hypotenuse. So this will be x here, and then the hypotenuse will be 1. And then now we're thinking, okay, well, this is the what? This is the adjacent side. So we say adjacent side squared plus x squared equals 1. You can probably do this in your head, but it's still the Pythagorean theorem. So now we have adjacent squared is 1 minus x squared. And so we select the positive radical. So the adjacent side will just be the square root, principal square root of 1 minus x squared. So really what you can do in your head is like 1 squared minus x squared square root, or the square root of 1 minus x squared. So now we have this. So again, this technique doesn't get a whole lot of use, maybe so much use in Cal 1, but it certainly gets a lot of use in Cal 2 when you do trigonometric substitution as an integration technique. And also when you're doing the derivatives of the inverse trig functions at the beginning of calculus 2. So now we're good to go. So what does this equal? So this implies we've got the triangle, and this will give us any trig function we want. So the secant of the inverse sine will now just be secant of theta. The secant of theta is just the reciprocal of the cosine. Cosine will be the square root over 1, so we do 1 over the square root. And this has the positive value that we're looking for, that we expect here. So of course it's not defined at 1 and negative 1. We get infinite. We get an infinite tangent, which we expect. So the idea is that not only can we do the calculation here for a real number, but we can do the calculation where we're just looking for an algebraic expression. And we see that the procedure here is exactly the same as it is here. The only thing that's changed is that the input is a variable, but you treat it just like you do a number. Just write it as a ratio. So this technique will be something we'll use again in this class, and of course you'll use later in physics and engineering and other math classes. So this is a nice technique. Now, again, why did we care about Professor Ron's lemma? Well, because the next theorem has to do with a theorem about triangles, and that's called the law of sines. And so you're thinking, if you have the law of sines, I guess you're going to have to deal with equations that have sines in them. And let's face it, yeah, we need that information. Now, when we get to more elaborate equations, we might have higher powers of sine, but when we reduce the factors by factorization, then we get the first degree factors that we've been talking about, where we have to do the same thing again. So the Professor Ron's lemma is really going to be an integral part of how we solve trigonometric equations, because if we ignore it, we leave out most or part of the solution, which is not good. Thinking, well, I keep missing this problem. Well, you're not using Professor Ron's lemma mainly, possibly. So 6.5 will be the law of sines. And this is an easy theorem to write. And it's a useful theorem that, of course, helps us solve problems about triangles where we have certain hypotheses. So when you have just a generic triangle, you think, well, how much information do I need to have so I can actually solve it? And we're going to review that. You did this in your high school geometry class. But what's our generic triangle going to look like? It's going to be real simple. So we'll have something that looks like this. So just do a generic triangle. So again, we're going to be lazy when we write this. We're going to say that A will not only correspond here to the vertex, but it will correspond to that angle. And then the side opposite A will be A, and that A will also denote the length like we did before. Again, this is abuse of notation, but it's a common abuse, like, you know, pounds and inches that we use from the English, and we're used to it. So we'll adopt that for this. And then of course we could have a C here as a vertex and an opposite side C of length C, and we can have B as a vertex and an opposite side. After a while, these Invisalign make it hard to speak, but I'll make it the opposite side B of length B. So again, angle B, angle C, just for ease of use. So that's our generic triangle that we'll use for the law of sines, and then right after this, the law of cosines. So now, when can we solve a triangle? So I'll just say this: solve a triangle. So these are the hypotheses that we can use. The first one is a familiar one. It's called angle side angle. If we have those hypotheses for a triangle, we can solve it. Either the triangle doesn't exist or we'll get a one triangle. Then we've got side side angle. Now again, we always run the risk that the triangle doesn't make any sense with the hypotheses. So that's always a possibility. But if there is one triangle, we get it in the first case. But in the second case, this is what we call the ambiguous case. So this is called the ambiguous case because, you know, you think, well, they're all ambiguous. You couldn't have a triangle. But I'll just say, when we have a triangle in 3 of the 4 cases, we get one triangle. This is where we have to think a little bit more. And this has everything to do with the sine equation in Professor Ron's lemma. So first, just like with any case, we could have no triangle. Maybe the hypotheses do not support the sine equations. And so we get an equation that has no solution. So if it has no solution, if the equation has no solution, then the actual geometric object does not exist. And then for 2, we might say, well, we just have one triangle. we look at the equations and we use Professor Ron's lemma, but one of the equations produces angles that violate the 180-degree angle sum. So we're always going to have two solutions with the Professor Ron's lemma with the hypotheses that I've set up, but the triangle, the second triangle may be one that's non-existent. That is, when you add up or you add the interior angles, you get a number bigger than 180. That Euclidean triangle does not exist. So that would mean one triangle. And then of course, maybe you checked the second solution and you actually derived another set of parameters that actually exist. That is, the degree sum makes sense. And so you get two triangles. So this is not a hard problem. It just means that when you start solving equations, you get two solutions, and you check one, work that out, and you check the other and say, okay, do I get legitimate angles or not? If you do, then you end up with two triangles. If one of the equations doesn't give you a legitimate triangle, you just get one triangle. And then of course the no triangle is the case with everything. And three, that is side angle side. That is, if a triangle is produced, there's only one. Again, that's fixed. And then side, side, side. Again, one triangle if it exists. Now, for 1 and 2, obviously, we can use the law of sines. But for 3 and 4, this requires a theorem outside of the law of sines called the law of cosines. So you can't work very well with 3 and 4 unless you have an additional piece of information that will require another result. So this situation here, 1 and 2, will be something that we can actually solve using the law of sines. And so maybe it would be good just to say, well, what is the law of sines? So let's write it down. So we've got this generic triangle, and what we want to do is apply, in this case, apply the area formula 3 times. So this is why I think this is an easy proof to remember. You can recite this in your sleep, so to speak. So we'll think of 2 sides included angle. So we'll start with included angle A. So area will be 1/2 B times C times the sine of the included angle, right there, using that angle with sides here. Now the included angle can be B if we use sides A and C. So we'll say 1/2 A times C times the sine of B. So that would be the area of this triangle, which would also correspond to this. It doesn't matter which angle you choose. Usually you just choose whichever sides you're given and you go with that. But abstractly, we can use any side. We just have to think, well, Webber-Sign gave us these sides and this angle, so we're forced to use them. Now here, we can use this included angle in A and B. So 1/2 A times B sine C. So when you look at this particular situation, you're thinking, well, is that the statement of the theorem? I mean, is this going to be what we need? Well, we want to clean it up a little bit. Notice the 1/2's absorbed throughout. So we get BC. So we'll say equivalently, BC times sine A equals AC times sine B equals AB times sine C. Now, this is one form of it, but it's not the most convenient form. And if you've seen this before, you see this doesn't look quite right. So what we can do is just divide the entire equality here. All of this equation, we can just divide everything by the same term, and we'll just use ABC. So when we divide by ABC, notice the BC's absorb, and we get sine A over A. So notice the opposite side and the angle correspond. Here the AC's absorb, and we get sine B over the side B. And here the AB's absorb, and we get sine C over the side C. So this is like really simple, but very powerful. You're thinking, well, we certainly had a good use for that area formula, and like, wow, how simple is that? Now, what I said before is that you can see now, if you have angle side angle, you can use the law of sines, because you can use the degree sum to get the third angle, and then you've got an opposite side and a corresponding angle. For instance, if you have angle side angle, you can get that angle, so you've got the corresponding opposite side, and then you can solve for one of the others. So that would just be one unknown. That's why this is really useful. And of course, if you have side angle, you're in good shape too. You have an angle and a side, and then you can solve for the angle. So 1 and 2 are perfectly made for the law of sines. 3 and 4 don't have that luxury. We need another, too many unknowns. For instance, when you use the law of sines, you've got to know everything for 3 of the 4. So we see that 1 and 2 help us out. So 1 and 2 are solved with this theorem. Again, using everything we know, the nice interior angle sum and things like that, assuming that we have those available, and we do. So like when you solve a triangle, once you know both of the theorems, you can utilize any one. Once you get the ball rolling, what's left, you can, well, let me just use this since I know it, kind of thing. Then you have more flexibility. But to get the so-called ball rolling, law of sines is fine for 1 and 2. And then, of course, the law of cosines is required for 3 and 4. Okay, let's do an example. And they'll just mimic what I was just talking about. So here, say we have a generic triangle. So here's an example. So now we're seeing that it's like we're back to general math. We're focusing on triangles in a sense that we're doing a lot of topics you did as a younger person before you knew the more sophisticated geometry from your high school course. So here, let's draw this. You don't have to draw the picture. I mean, I'm just kind of drawing a picture that Webassine gave. So we have A, I'm just drawing a generic triangle. So here's the hypothesis. This is what we're given for the generic triangle. That is, we have A is equal to 52 degrees. We have B is equal to 70 degrees. And we're given that the exact measure of side C is 26.7. So these are all exact, okay? It doesn't matter if you do this and for some reason, it's like, again, when you see this, that number is exact. That's 26 7/10, okay? That's an exact number. I don't care if it has a decimal in it, it's exact, it doesn't matter. That doesn't mean that you write your answer as an approximation. What it does mean is that you use that as an exact figure in the problem. And then if the problem says approximate to 1 decimal place, you can use your Google calculator to get there. That's what that means. So now, when you look at this, this is just like what we had before. We have angle, side. And the key here is that when we think about this, we look at this and think, okay, not angle, side, angle. So right over here, angle, side, angle. So that's good. We can use the law of sines. And so now the first thing we want to do, which is what I said before, is that we can figure out the angle C. So now angle C will be 180 degrees minus the sum of the other two. So very simple, 52 degrees plus 70 degrees. So we get 180 minus, and we add these, we get a 2. So that's a 12. So 60, so that'll be 60 minus 2. So that's what, 58 degrees? So now, and here's what the problem says. Let me write it down. It says compute, I should have written this first, compute A, and then it says round to 1 decimal. When you read these problems, read them. Don't, a lot of times in conference hours, I'll listen to what the student says and I'll go to the WebAssign, keeping that on my brain, and I don't read the problem. Then I go back and say, wait a minute, the problem said this. So we all fall victim to being conditioned. So when you read that problem, read what, if you need to write a function, what in terms of what? Theta? So put thetas in the equation. Don't put x's and y's. I mean, follow what the directions say. So now, when we look at this, we have angle side angle. So we can say, in this case, sine C divided by C. And then, since we need to know A, we'll use sine A divided by A. So use law of sines. So this will be sine C divided by C equals sine A divided by A, where A is the unknown. So if you want, go ahead and flip everything around. So we have A over C equals sine A over sine C, just using laws of the proportion. And then, of course, if you like, we can cross multiply by C. So A equals C, I'll use a little dot, times sine A divided by sine C. Now, again, just for ease of use, degree mode. Because if we need an approximation and we're given everything in degrees, then we want our answer in degrees. So let's just go ahead and use the degree mode with the Google calculator. So now, so this will say A equals what? So equivalently, we have C, which is 26.7 times sine of A, sine of 52 degrees, divided by sine, in this case, of C, which is 58 degrees. And this is exact. This is exact. But now, of course, our client would like an approximation, so we can go to our Google calculator. And so again, DEG for degree mode. So we'll have parentheses. We don't need it, but it's good to over parenthesize when you're doing this, so you're sure. Don't do it to the point that it makes things wrong, but this is fine. 26.7, because we're only dividing by one number, but this is better for you to overdo it than leave it out in the future and get an incorrect answer. And then sine of 52 degrees, close, divided by sine of 58 degrees. Now, the beauty of the Google calculator is that once we use the degree mode, we don't have to put in the little 0 there, the little O superscript. It knows what we're doing. And so, again, just be aware that when you're stating an answer, you need to use that little superscript so WebAssign knows it's a degree and not a radian. So now we get 24.8097, etc. So we're going to round to 1 decimal and get 24.8 degrees. So again, one thing about the technology, I mean, is that it does at least allow us to get to a very, very reasonable approximation, a very, very good approximation. Again, this is the best. This is an excellent approximation. There is no approximating in this problem. This is an exact answer here. And so when we get to this, we are assured that we have an excellent, excellent 1 degree approximation. And of course, you know, if this is sufficient for your surveying, which it probably would be, then you're done. So again, angle side angle, easy way to utilize the law of sines. And then of course, lastly, if we don't have B, we can easily solve for B using any set here. You can use angle A, angle C, angle B and angle A, or angle B and angle C. As long as you have the B in it, you can get little b. So again, the law of sines, very user-friendly here. Now, what I want to do is look at an example that actually utilizes some of the constructs that we've already talked about, but it's an interesting problem. And it actually has lots of really good ideas in it. And so I want to do it. Now, what are the hypotheses here? For instance, let's look at this problem. We have a triangle within a triangle like we did last class. And one of them is isosceles. So we're going to try to draw a nice picture and use the arithmetic with the picture to kind of coordinate everything. So we're going to get our isosceles part. So here's our first triangle, and our second triangle runs this way. So what we have, what do we have here? Now you're going to think, oh man, I got all these triangles here, and you got all these letters. You're going to drive us crazy with the letters. No, I'm going to make it easier. We're not going to do angle CBD like you did in high school. We're going to keep it simple because we want to keep our sanity. So here's the hypothesis. We're given the following parameters for this problem. This is going to be isosceles. I drew it that way, but we have a side of 19 units here, and we have a side of 19 units here. Okay, and then this side is 27 units. So what we've drawn here is very, at least, you know, interestingly correct in the sense that we have this larger side. So this obtuse angle makes at least intuitive sense. And then we're given that this is a 30-degree angle here. So when we think about this, you know, we could just move this over and create, you know, a 90-degree angle if we wanted to. So we can clearly see here that this angle is obtuse. This angle is in the second quadrant, so to speak. So we need to keep that in mind when we do our computations. Now, this is the given. Hypothesis is given. This is it. That's what we have. Now, what I'm going to do is I'm going to write in some other things. I'm going to write in an angle here, alpha. That's angle BCD, and then angle DCA. But I'm not going to call them that because we want to keep our sanity. I'm going to call this angle beta because, again, we want to be efficient. It's not going to affect anything. So what we want to do, and this is what the problem says, compute alpha and beta. Compute those angles. Now, another thing that's going to help us out so we don't have to say angle CDA, I'm going to call this angle theta. Now, I know this is a supplement to this. I'm not going to worry about that right now. Later on, I'll use that. But these are base angles of an isosceles triangle. So they are congruent. So I'm going to call both of these phi. And you're thinking I could just go ahead and write that in terms of theta. as 180 degrees minus theta, which would be fine too. And that would be a shortcut, but I don't want to clutter up the picture. We'll keep that in our back pocket and use it as we need to. So now when we look at this, we're thinking, well, we're good to go because we've got all kinds of good stuff here that we can use. We've got for instance, an angle and the opposite side. And then of course, we're thinking, what can we do to get beta? Well, we can use the law of sines in the sense that now I've got this angle opposite here and I can figure this out. So first, what we want to do is denote this as triangle 1 and this is triangle 2. Now, when I looked at this problem, I thought, well, I'm going to do 2 first. If a Webber-Sign problem says, what's this, but it's easier to start here than do that first, then work backwards. I mean, there's nothing wrong with that. So I'm going to do that. But what I'm going to notice here is that when I actually solve this, I'm going to think about exactly what I'm doing and what it means in terms of the law of sines. So now if we see, we have sine of 30 degrees divided by 19. So let me write up here, use law of sines. So we have sine of 30 degrees divided by 19 equals, now we've got sine of theta divided by 27. So again, we're thinking degree mode. We're thinking of all of our angles being measured in degrees just because we're going to think about using our Google calculator. So now we can solve. Let's just go ahead and cross multiply. So if and only if sine theta equals 27. Now sine of 30 degrees, that's just 1/2. So that's times 1/2. If it's easy, it's easy. So let's take easy. And then we have what? We've got a 19. Now notice when we divide by in this by 2, we're just multiplying the denominator by 2, and that gives us a 38. So this is 27 over 38. Now, notice here, we have sine of theta is equal to 27 over 38. So we can actually solve for theta using the inverse sine function. So equivalently, theta is equal to inverse sine of 27 over 38. Now, let's think about this. Where is the inverse sine located? That is, when we think about inverse sine, let's write back to our very beginning here. That is, notice the inverse sine of x lives between negative pi over 2. So it lives between negative pi over 2 or negative 90 degrees and pi over 2. So this is positive. So when we look at this, we're saying that this is going to be an angle between 0 and 90 degrees. This is an obtuse angle. So now we're going to have to make a little bit of an adjustment here. So when we think about this particular value here, we need an adjustment. So I'm going to think of this as a theta 1, and theta 1. So this implies that our actual theta, which is obtuse, will be 180 degrees minus the acute angle, which is Professor Ron's lemma for the upper arc, which will be inverse sine of 27 over 38. So this is what I mean when it comes to analyzing with the law of sines or anything. We have to respect the inverse trig functions, because now we see that the actual theta is that value. It's an angle that's in the second quadrant. So we can say this is in the second quadrant. So when I said you need to learn your inverse trig functions, I was not fibbing. This is so important that otherwise when you do these problems, it'd be like having blinders on. You won't have any idea what you're doing unless you respect the inverse trig functions. And so now we have this angle, and we know that the sum is 180 degrees. So now this implies that beta plus theta plus 30 degrees equals 180 degrees. So we can easily solve for beta. So beta equals 180 minus, now we can go ahead and substitute for theta. So this gives us 180 degrees minus inverse sine of 27 over 38, again, minus 30 degrees. Now, when you do all this subtracting, notice the 180s absorb, and you get here, you get a minus minus here, and then a minus minus here. So this gives us 30 degrees plus inverse sine of 27 over 38. Oh, and here, sorry, this is let's see here, we've got the 180. So let's just check here to make sure that this looks good. So we got beta, so 180, and let's see. Oh, that's a plus here, sorry. That's a plus, that's a negative here. We need that. When we run everything over and we factor the negative, we've got that. When we take this over, notice that becomes a plus, so I need the minus minus, so that's a negative. So that's an important negative there. So now let's see what this is using our degree mode. So now, Google Calculator. So again, DEG for degree mode. So we have negative 30 degrees plus inverse sine of 27 degrees divided by 38 degrees, or excuse me, 38, not degrees, 27 divided by 38, but let me clear that out. Divided by 38. And this gives us 15.2777. So in this case, round to 1 decimal. So this will give us 15.3 degrees. So again, what you see in this particular problem here is that when you work this example, again, you apply the inverse trig function, and then you say, okay, well, now that I have all of these angles here except for beta, I use the interior sum and take the difference, and then I get my angle exactly. And now for the other part, now that we've done 2, 1 is easy. So note that when I add these 2 angles in alpha, I get 180. So now 2 alpha plus, excuse me, 5 plus alpha equals 180 degrees. And so now alpha equals 180 degrees minus 2, 5. But now what we see is phi is just the theta 1. That is, when we look at this, this is the acute angle, which is this guy right here. So we get 180 minus 2 times the inverse sine of 27 over 38. This part. So using the fact that this is an isosceles triangle and the fact that these are supplementary, we have another exact calculation. And we know what that is, but I didn't save it. So let's just go back and recompute it. So again, make sure you're in the degree mode. So we have 180 minus 2 times inverse sine. So do your inverse for arc sine And then we have 27 divided by 38. And this gives us 84.444, etc. So we got 444, etc. And if we round to one decimal, that gives us, oh, sorry, 89. Too many fours. So that gives us 89.4 degrees. So what I like about this problem is that it pretty much showcases everything that we need to know about inverse sine functions. Look at this. We've got a rather complex diagram here, but if we break it down to do 2 first, we can get an exact calculation utilizing the inverse sine function, but then of course noting where this actually is going to live and making the adjustment to get the second angle, excuse me, the second quadrant angle, which is the obtuse angle. That is an angle between 90 degrees and 180 degrees right here. And then using the angle sum here to get beta. But then once we have that and we know that this is an isosceles triangle, we can again use the interior sum of 180 and boom, there it goes. So hopefully this is fun. These are fun computational type problems, but again, when you do them with the symbolic calculation mode, they're actually very precise and they actually help you understand the inverse trig functions better. The beauty of the inverse trig functions is only realized as you apply them. And that's where I see the benefit of doing the law of sines and the law of cosines, even though you don't spend a lot of time with these theorems in calculus, but you do see them in engineering. You do see them in physics. And so that's why we covered them here. But with that said, you can study geometry all day long and never get bored. So that's a fun problem. Now the very last one, again, is another law of sines, and I hate that I have to try to do some decent artwork, but you know, artwork is what is it in the eye of the beholder, the quality of it. So in this last problem, this last example, I thought was kind of interesting. The way it's stated, ladies and gentlemen, it's given in the form of a story problem. And so what I wanted to do was maybe draw a picture to make sense out of it. So we're going to have a shadow that a tree casts. Sun is shining on the tree and it's going to cast a shadow of 230 feet. And then the slope with the horizontal, I'll draw the picture, the slope with the horizontal will be 26 degrees. And then the light beam of the sun, the light beam with the horizontal, so these are triangles within a triangle, will be 56 degrees. Now, here's the picture. So this is the hypothesis. So we've got a tree, and I'm going to go, let me go ahead and draw the horizontal. And for instance, here we've got this slope. That is, we've got this nice slope where the tree lives. Say a nice Christmas tree. So here's our tree right here. Right there. So there's our tree, and it's going to have a height we're going to call h. You're thinking that's what we're going to have to compute. You're exactly right. So that's h. Let me little space there so it doesn't look like the h is running into the line there. That's h, a tree of height h. And then, like I said before, we've got this light beam The sun is up here, and it casts a light beam by the tree to the very from the top, right there. And then we've got the slope here runs this way. The slope of the mountain runs this way to the bottom of the tree where it's situated. Right there. So as the beam comes down, the tree casts the shadow right here. And the shadow is 230 feet. That's the shadow right there. And then the light beam with the horizontal, we'll just put this right here, is 56 degrees. And then the slope of the mountain with the horizontal is 26 degrees. And this is, so we can solve the problem of right triangle. So that's the picture that's given in WebAssign, and they give this, but I want to try to make it a little bit more realizable. And so now, when we look at this, we're thinking, okay, well, we can figure this out if we can set forth with the law of sine. So let's go ahead and write in what we will know here. Notice this big right triangle has a 90-degree angle and a 56-degree angle. So we can get the angle right here. If you want to just go ahead and draw in the vertical, we can call this beta. So we'll say beta plus 56 degrees plus 90 degrees equals 180 by the interior sum. So beta plus, so that's going to be a 6. So a 146 equals 180. So now beta will be 180 minus 146. So that's a 40 minus a 6, which is what, a 34. So beta is 34 degrees. So if we have the 34, we've got the angle opposite the shadow length 230. So the only thing we need to apply the law of sines is this angle, and that's easy. That's just 56 minus 26. And that gives us 30. So right here to here is 30 degrees. So the way the problem stated, it seems really complicated, but it's not. This is where, if you were a surveyor, you would certainly like to have in your hip pocket your formulas from pre-cal and your tables of trig values, or your handy Google calculator on your phone, okay, to make your computations. So your boss will give you a raise. And so now by the law of sines, this is fun. It's like doing general math, but with the college twist, so to speak. So now we're going to have sine of 34 degrees, sine of 34 degrees divided by 230 equals, now we've got sine of 30 degrees. Well, that's our friend from the unit circle, divided by the opposite side, which is h. So now we can flip things around. So we have h over 230 equals 1/2 divided by sine of 34 degrees. And then lastly, h will just be 230 times 1/2 divided by sine of 34 degrees. But that's easy to compute. So that's going to be a 1 and a 5 divided by sine of 34 degrees. So we've reduced this problem to a triviality with the law of sines. So I think I have to, like I say, these problems give me an opportunity to give you more information about how the inverse trig functions work. So I applaud the triangle theorems when there were times when I didn't, because I thought they just got in the way, but I had to think about it and present these problems in a way that will help you get better. And that was really based on the fact that I designed honors courses for every class that's taught at San Jack. And then it helped me to realize how to recast my regular classes to make them even better. And so, you know, there's always a way around things. Don't just criticize something, work with it and fashion it into something that will get you in a better position. And I always think about what my students need, and they need good math professors who understand what they need to become good STEM professionals. So now let's be a good STEM professional and make sure we're in the degree mode. And we have 115 divided by sine. Well, this is so easy. It's like we can do this in our sleep, sine of 34, and be very thankful to our friendly neighborhood Google calculator. So this will give us 205.65. And in this case, we round. WebAssign said round to nearest foot. So this will give us 206 feet. So when you look at these types of problems, maybe you should kind of rejoice and say, well, we got a little bit of break from the tedium of Professor Ron talking about theoretical constructs, but we see here that the understanding of this problem and even this problem here require that you have a theoretical backing. Again, when you don't understand how things fit together, how can you possibly understand what you're doing? A student one time told me that they didn't need theory to do math. And I said, well, how did you solve this equation? They said, well, I used the quadratic formula. I said, young man, that's a theorem. So if I take that away from you, how do you solve it? He says, I don't know. I said, well, then what you just said is incorrect. So, ladies and gentlemen, understanding the mathematics is tantamount to understanding sufficient amount of theory so you can do the problems and be a successful STEM professional. So I would be selling you a bogus bill of goods to just say, just memorize this stuff. The memorization will get you absolutely nowhere. It will help you, however, if you've memorized the unit circle and you've memorized the inverse trig function domains and range, that's really good. Because if that's right there on the tip of your brain, that's excellent, but you have to learn how they synthesize. So I hope you've enjoyed the little departure from the regular tedium. We'll do some more of that with the law of cosines, and then we'll do some trig identities, which I think you're really gonna like. They're gonna be fun and basically use what you already know. So I appreciate your attendance today. Remember, I'll have up an announcement tomorrow that outlines the items for the test and the window of time to take it. It'll be similar to the last test. And again, if I don't see you at the conference hours, I look forward to seeing you next week. Stay warm. Have a great rest of your day. We'll see you later.
Thank you.
Thank you.
Bye, thank you.
Bye, everyone.
Bye, thank you.
Thanks, Marin. Sometimes I don't know when you all speak, your mics say they're silenced, but I appreciate your comments. You're very kind. Bye.